All right, so this is our VR movie of our model selection algorithm. We just started moving into the data analysis and data visualization using virtual reality. And so our first approach at it was model selection, where we, in our modeling methods of our analytical chemistry data, we create millions of models, and typically what one does is try and select a best or good model. And our approach is to select a collection of models that have model diversity, and yet they predict our analyte concentration, typically, is what we work with, the same as we'll see. All right, so this is what we'll see in our VR at the beginning of the movie. And we have two landscapes for all the models. And on the right here are the prediction errors, color coded, to our training samples. And in these cases, these training samples, we know the analyte amounts, concentration typically, that we want to try and predict. And this is how we form our models with those training samples. We have our analyte amounts. Typically, we work with spectra. So we have our training samples, spectra, and then this is our model. And so we need an estimate of this model, the regression vector. And so we do a least squares fit. Typically, we use partial least squares to get this pseudo inverse. And then once we have an estimated regression vector, we can inner product that with our target samples spectra, and we get the analyte amounts. And hopefully these estimated amounts are close to truth. So when we're doing our training samples, these would just be training samples, and we get the estimates of our training samples, and these are the prediction errors. And on the left over here are the actual prediction errors of those target samples. So they're like pseudo target samples. So we can see how we do. And so what we want to do is pick the better models that obviously predict the training target samples well, without knowing that we're doing that. And so those are the regions these are the lower regions, the blue with the lowest prediction error on the target samples. And you can see the training samples, the better models are back here on the training samples. And but so these are the models we want to end up with. They're kind of from the color bar. You can see they're intermediate models I call them intermediate models because they have an intermediate prediction error. They're not the best, they're not the worst, they're okay. And those are the ones that actually predict the target sample well, typically. And anyways, regardless, we have these three coordinates axes that are the same in both cases. And this is what gives us our shape to our landscape that allows us in VR to identify these better predicting models. And so we do have this U curve. And so when we zoom in, you can kind of see it here that there's a lot of curvature throughout the landscape. And that's due to this U curve, which guards against over and under fitted models. And then we have our cosine theta, which is our model diversity. Because again, the idea is that these model pairs, each of these glyphs represent a model pair, that they have diversity, and we do. We have quite a large angle between the two regression vectors, and yet they predict similarly. And how well they predict similarly, again, this would be our target sample prediction difference. And so these we know, these are the target sample prediction differences, and so these are the models that are predicting the target samples similarly, and yet they have model diversity. And we have this curvature which pushes them down to the bottom of, that's what we call them, U curves. Those are the models we want down at the bottom of the U curve. Again, we have this autonomous algorithm with some generalized threshold. This is for model diversity. This is what we used. And so in the VR, we're going to go in and predict these samples. And I don't think I mentioned what this box was. That's our model elimination box, so we can eliminate thousands and thousands of models all at once and hopefully zoom in on the ideal models. So these are our glyphs. They're simple ball with spikes. And so we have 8 measures of model quality for our pairs. And so if they're poor quality measures, the values are large, then we have these star shapes, and those are poor models. So these would be bad models. Even though these are intermediate models, the greens, they're still in this star zone, and they're not in the lower U curve, and they are rough, very rough looking, and have the stars. Ideally, we want the model quality measures to be small, and that gives us our smoother sphere, and those are the good models. And so you can see, you can still have some perhaps smooth models up here, but they're not the right color, or they're not in the right region. So what we do with the VR is we get spatial position of our model pairs, plus we get shape. And that's what really helps us in the VR, is in our data visualization and our current work on classification, is we get shape. And so we can get the spatial relationships, as well as get an idea of what the shape of that glyph looks like. And we can leverage that in VR. So this is how we did. Here's 10 samples in that target batch. And so we selected the models, the diverse models that predicted these samples similarly. And so these were our final prediction errors for those target samples. These were our MDPS, the blue line, our prediction errors. The dashed lines are the mean values. And so you can see our prediction error is lower by selecting the models in VR for a bunch of samples all at once. And our R-squareds are better too. And so typically when we select models in VR, if MDPS with this generalized set of thresholds, if it's doing very well, we do well too. And when the MDPS is not doing well, we do better. And that's the advantage of the VR, is we can get to those situations where the autonomous algorithm does okay or not great. And in VR, you can always beat that. So this is the movie. So it's just showing in the VR how they do overlap, because they have to, because it's the same 3 coordinate values. The only thing changing are the color bars. So the left, the target samples, we don't really know what that is, so we'll set that aside. And these are our training samples, and yet they do have the target information in there, because they do have the prediction differences of the target samples. So, but no prediction error. So this is, with VR, you can zoom inside the data cloud and look inside and out. And there's that curvature that I mentioned from the U curve. So here's our model elimination box. So we can start chomping away on those rough looking models, and especially those that are in the models that have very high similarity. And we want model diversity, low cosine theta. So we'll get rid of those models and so forth. So those were our final set. So here he just overlaid them again, and showing that, these intermediate training sample prediction errors are right there where we want to be for the target samples. And so we end up predicting the target samples very well. So again, all the information on how we build the model, more details, and the model updating, and the different data sets, what the data sets are, and so forth, are all in this paper in Applied Spectroscopy. And there isn't a companion virtual reality movie of our that goes with this paper, and that's where we can touch the glyphs, and we want to be able to see the regression vectors, just actually visually see the model diversity. So we needed a way to represent this a vector into a three-dimensional space, and that's what that VR movie is all about. And if you have questions or you can email me, and I can, if you can't find this paper, I can send it to you. Okay, well, thank you.